So we'll start maybe with the second paper. It's about, entitled an improved random shift algorithm for spanners and low diameter decomposition.
All right, thank you for the introduction. So our paper is called an improved random shift algorithm for spanners and low diameter decompositions. And this is joint work with Sebastian Forster and Marc Grösbacher, who's present here. So please direct all your questions to him after this talk. Let me first give a little outline. So the algorithm I will present today is a clustering algorithm. I will give some more details about what that means. And it has three corollaries. One of them is the spanner, one of them is the synchronizer, and one of them is low diameter decomposition. And personally, I think the spanner is the most interesting. So this talk will focus on the spanner and we'll show how it works for a spanner. And then the other two I'll just mention at the end very briefly what the result is, but won't go into the details. Right, so refresher, a spanner is for a graph, a subgraph, where we take some edges but not all of them, and we want to maintain the distances. So we say that the spanner of stretch alpha maintains distances up to a factor alpha. So they might become a little bit longer. And in this particular picture, it should be a spanner of stretch 4, I think. Of course, people make mistakes. So go ahead and see if you can check it. See if you can find the distance and see, well, if you take only red edges, you should get the same distance within a factor 4. Spanners have a wide range of applications in graph theory. For example, in approximate shortest paths, in distance oracles and labeling schemes, in routing, in spectral sparsification, and many more. Especially, I think, in distributed models, they're very important and very useful because these sparse properties are very useful for anything where you want to do something, where you want to distribute any information over the graph. That's first some existential results. So already in '93, Althofer and others proved that a greedy algorithm can give a stretch of 2k minus 1 with this size bound, n to the power 1 plus 1 over k. And this is actually optimal, proven way later by FNS. And the reason why we take stretch 2k minus 1 is because the bound looks pretty on the right side. So it's a combination where we always look at this type of bounds so that together it looks kind of pretty. Let me say something about the model before I go into which results are out there and how our result compares to that. So we will talk about the CONGEST model. CONGEST model is a model where we look at a set of processors that are connected by some communication links. And we model this by a graph with n vertices and m edges. And each of those processors has a unique ID. Meaning that they know this at the start of the algorithm or at the start of the rounds, and they know which neighbors they have, but there's no global knowledge of the network. We do communication in rounds, where in each round there's unlimited internal computation and message passing to the neighbors. Those messages have a bandwidth constraint and the name CONGEST of log n bits, which I think is mentioned earlier, means you can send some node IDs or some edges to your neighbors, a constant number in each round. And the complexity we consider is the number of rounds. So that's what we want to try to minimize. In general, we don't care too much about how many messages there are, but that's a second order complexity measure. And the objective will be to solve some theoretical graph problem on the communication graph. And in this talk, this will be completing a spanner on the communication graph. All right. The results that are out there about this are, first of all, an algorithm by Botswana and Sen that always works. It always gives you a spanner of stretch 2k minus 1. And the expected size is k times n to the power 1 plus 1 over k. So if you remember, this is a factor k too big compared to the optimal bound. It takes O of k rounds, so it is quite fast if you want to have a spanner with low stretch. Miller, Peng, Flado, and Xu showed that you can improve on this, but the stretch is not optimal anymore. So you get a sort of optimal size, but the stretch is off by a constant vector. I think it's something like 4k, if I'm not mistaken. The number of rounds maintains the same. Elkin and Nyman later showed a result slightly improved on that. It gets stretched back, but now it doesn't necessarily have the right stretch. So with the probability 1 over c, the stretch is too large. And if you look at this, you can see this is not with high probability result, because if you want c to be really big, the expected size goes up. So this is only a constant probability result for the right size. Our new result shows that you can maintain a stretch of 2k minus 1 with probability 1 and get the expected size you want in the right number of rounds. And this might seem like a small improvement, but I think we're making big steps towards the really optimal result here, and that's why it's really important, and we're narrowing down towards the final solution for this answer. A few things to notice maybe is that the number of rounds is always the same. There's a good reason for that. So the number of rounds, of course, approximately the same. There are some constant vector changes. But the reason for this is that all of these algorithms are clustering algorithms, meaning we grow some clusters that have low radius, and then we connect the clusters, and together that forms a spanner. Especially the last three are ball growing algorithms. And I'll first give you an intuition what that means in a sequential setting, which is a little bit easier than distributed setting. All right, so we look at same graph as before. Now we want to compute a spanner of stretch 3, which means k equals 2, if you want to have a 2k minus 1 spanner. What we do is we are going to grow clusters with radius 1. 1 is k minus 1. I took a green vertex, and I'm going to grow a cluster, meaning I just get all of its neighbors. And together this forms the green cluster. Now I take any next vertex. Here's a red one, and I'm going to look at this neighbors. And I didn't take all of its neighbors. I only took the neighbors that haven't been appointed to any cluster yet. There's one of its neighbors that's already in the green cluster, but we ignore that one. We just take the remaining ones. Now take the next one, a blue one, and a few neighbors left. One more, take a violet one, and its last neighbor. So we have 4 clusters here, and it doesn't really matter that they become smaller. What's important is that they all have radius 1. And now we connect those neighbors to each other. We don't add all the edges in between. We just have to add one edge to each neighboring cluster for each vertex. And I will first explain why this is enough, and then explain why this is sparse. And as you can see here, it does become a little bit sparser, even in this small example. And the general idea will be that we have clusters of radius 1. We have one edge between clusters, then another cluster of radius 1, which gives together a distant estimate of 3, and that's the stretch 3 we wanted. In more detail, I first need a slight remark that it suffices to show the property we want only for the edges. This is not very hard to see, because if you have a shortest path in the original graph, you can apply the triangle inequality to get it for each edge, and then apply the definition where you have it only for the edges. So this is not too hard. Okay, so let's look at an edge UV. We want to show that this will have stretch at most 2k minus 1 in the spanner if we have clusters with radius k minus 1. If UV is within one cluster, it's quite easy, because if we have a path from U to the center of radius k minus 1, so that's length k minus 1, and then we go from C to V, which is again k minus 1, and we even have some room to spare. Suppose there's an edge between two clusters, from U to V, and they both have their open cluster center. Maybe the edge UV is not in the spanner itself, but as I said, each edge added a vertex to each neighboring cluster. Clearly they're neighboring clusters, so there must be an edge from U to V prime, where V prime is in the cluster of V. And now there's a path consisting of the edge U V prime to CV, and CV to V. And that's of length 2k minus 1. Now, if you want to do this distributedly, of course, we don't want to do it sequentially. That's going to be really, really slow. If you first grow one cluster and then the next, it's going to take forever. Instead, we want to grow multiple clusters simultaneously. And we do this with a random delay. The idea is that they don't start all at the same time, but there's a random delay or random shift at which they start. And if you pick those correctly, then it all goes well. Well, what does picking them correctly mean? Good question. In our case, we sample from the geometric distribution that we cap at the radius. We just have normal random distribution in the top line here. And then whenever you get a value that is bigger than the radius, just cap it off and you throw it all in the last bin. So there's a relatively high possibility that you get the value of the radius itself out there. Relatively high is still really, really small if you pick P correctly. In previous work, there were other distributions used, and that's our main improvement here, that this is a cap distribution, so it really ensures you that you never have a radius bigger than R. We have this random delay R minus delta V is between 0 and R, so the random delay is at most R. That means that within R rounds, each vertex will start a cluster growing, so if it's not in somebody else's cluster, it is its own cluster. So within R rounds, we're always done, as opposed to Elkin and Nijman, who might needed more things because they didn't put a cap on their distribution. All right. So final thing, we need tie breaking by ID. The reason is if I have a line here and I have two clusters, V3 and V7, that start growing at the same time, you get one step further, and then in the next round, they are fighting over you. You need to decide which one wins. And we say that V3 wins because 3 is smaller than 7. So we compare the cluster centers, their IDs for the tie breaking. It's important here that we use the cluster centers and not just the previous edge on the shortest path, but I can't go into those details in this short talk. All right. Let's go to the spanner algorithm as it is for the CONGEST model. We set R is k minus 1. I've said that before. Our radius is going to be k minus 1. And P is our control probability. Each vertex locally samples delta V, so they can do their random delay. And I'm going to give you a slightly different view, which I think is easier to grasp. And that's we add a conceptual vertex S, where we set the delay as the distance. So that looks like this. We have S, and then we have here the distances. And you compute your whole graph. Every edge has, or every vertex has an edge to S, but some of them are longer than the shortest path. So this is what the shortest path tree is going to look like at some point. And now, for the clustering algorithm, we output everything except the conceptual edges, which means we already immediately have branches of the tree that become our clusters. Besides those clusters, we needed intercluster edges. The intercluster edges were for each vertex, one edge for each neighboring cluster. I'll give you a picture. Take one vertex, take the neighboring clusters, and for example, to the left cluster, we take an edge. To the right cluster, we take an edge. If we don't have to take both of these edges, one of them is enough. That's going to sparsify it enough. We don't need any edges that go up 2 layers. The reason is, if there would be an edge going up 2 layers, then the level of this vertex would be one higher in this tree. So the only edges that can appear are either on the same level or one level above. And this we can actually bound. So we have to show that there are at most n to the 1 over k neighboring clusters for each vertex. And if we use the random delay and tie breaking, we can show that we can bound this number because you can only go up one level or one to the side. And that together is going to give a pretty sparse graph. And the theorem we end up with is this one. You can compute a spanner H, which stretch 2k minus 1 and expected size n to the power 1 plus n over k. And this runs in exactly k rounds, we didn't even need the constant factor. All right. There are two other applications of basically the same algorithm. We take the same algorithm, but we output something slightly different. One of them is in synchronizers. The synchronizer is the goal to have a synchronous congest algorithm run on an asynchronous congest network. If the synchronous algorithm has r rounds and m messages, then we can get r times k rounds, then m plus r times n to the power 1 over k. So that's the size. The size is an expectation, while the number of rounds is always k. It's exactly our result. And this is quite a standard thing. If you have a cluster-based spanner, you can always use it to get a synchronizer. So this is more of a corollary, and that is a very new result. But it's just the way how spanners can be used in synchronizers. But only certain spanners, because they have the need to have the right structure. Note that there should be an initialization phase. You have to construct the spanner first before you can use it, which uses k rounds and k times n messages using an auxiliary synchronizer, the alpha synchronizer, in case you're familiar. Another example is the low diameter decomposition, which is quite similar. You take clusters, and the goal now is the clusters have small radius, or actually small diameter. But because we have small radius, we have small diameter, and we want few intercluster edges. So to be precise, we can get clusters of strong diameter at most log n over beta, where each edge is an intercluster edge with probability at most beta times the weight. So this actually holds for weighted graphs, or previous results were just for unweighted graphs. And this runs again in the same number of rounds as our radius, which is a factor 2 off with the diameter. So to conclude, this is the spanner, this is our main result. We achieved this using the cap geometric distribution and a tie-breaking rule, which actually shows that you need less randomness than in previous algorithms where they used an exponential distribution. And we just need something that is discrete, which I think fits better with the nature of the problem and also avoids problems like how many bits do you need to send in a message? Because if you use an exponential distribution, of course, you have infinitely many bits. It's going to be a problem. You need to sample finitely many of them and decide how many you need to send to your neighbors to tell them something about the size. But by using something that's discrete in nature, you don't have those problems at all. So there's no implementation things to consider anymore. An open question is, of course, can we get this deterministically? That would be really nice, because now we have an expected size. It would be good if everything would just be deterministic. But for that, you would need some new techniques, because random shifts, of course, are random. Thank you for your attention.
So I think now the first speaker of the session is ready on Zoom, so we'll go back to the third speaker after. So we'll start. So I think Amir is here. So Amir will talk about a paper entitled Beyond Distributed Subgraph Detection, Induced Subgraphs, Multicolored Problems, and Graph Parameters. So you can start.
Okay, so do you hear me very well?
Yes, very well.
Okay, hello everyone, it's Amir Nikabadi. Today I will present a joint work with Janne H. We introduce our new result on induced subgraph detection in CONGEST model. So let us begin. For the sake of clarity, let me start with some basic definitions and setting. As our main setting, we are working on a CONGEST model when we are given a graph of n nodes connected by communication links, and the nodes may send the message up to log n bits to each neighbors at each round. And what we want to solve is induced subgraph detection. In particular, we are given a graph G and a fixed pattern graph H, and we want to know if G contains H as an induced subgraph or not. And by induced subgraph, we mean we allow to delete the vertices of the graph. But if you want to delete the vertex, we also need to delete all the incident edges to that vertex. For example, here for given graph G, this graph is an induced subgraph of G because we can obtain this graph from G by only deleting this vertex. But this graph is not an induced subgraph of G because to obtain this graph from G, we need to delete this edge and that edge, which are not allowed. In the case of translating the problem for the congest, we need to the nodes of H known to all nodes in G. For the case of prior work for subgraph detection in congest for finding non-induced subgraph, we have the noun result for even and odd cycle detection, and also the following upper bound for triangle detection. And in the case of prior work for detecting induced and non-induced subgraph for non-distributed setting, we can get different type of results for different H. For example, when H is pass or cycle or tree. But there's some pattern graph H with some good structural property, which we are able to design efficient algorithm based on method in parameters complexity. For example, for pattern graph, with a small tree bit, we are able to design efficient algorithm. Although there are still some pattern graph which a problem remains hard on them. For example, when H is a k-clique or induced pass of length k. Okay, in this paper, we have 4 kinds of results. We take the advantage of structural parameters to design the efficient algorithms in congest. And then we generalize our result for general graphs. And since we have relative multicolored version of problems in non-distributed case, so it's natural to ask about multicolored version of induced subgraph detection in congest. And at the end, we studied a new problem of maximum common induced subgraph detection, which we are given 2 graph G1 and G2, and we are looking for a graph G prime, which appears as induced subgraph of both G1 and G2. So in this talk, we first start by detecting induced K-tree and graph of bounded degeneracy. Let me recall that the degeneracy of the graph, a graph G is called D-degenerate if every induced subgraph of G has vertex of degree at most D. For example, forests are 1 degenerates and planar graphs are 5 degenerates. For the graph of bounded degeneracy, we presented deterministic algorithms for finding induced tree of K nodes on graph G. The algorithm takes function of D and K plus log and rounds in congest model. For the case of other results, which will be a skip in this talk, we have the following unconditional lower bound for induced even cycle detection on general graph. It's n over log n rounds in the congest. And we also need to mention the independent and parallel work of Legal and Miyamoto, which appeared in ISAC 21, and they worked on induced K-cycle detection. Okay, so let's start with details of our first result. Back to our goal, we want to find induced K-tree and graph of bounded degeneracy. The degeneracy itself has been studied very well in the distributed settings, but in our case, it's also interesting because, as we already mentioned, we know that there are some useful method in parameterized complexity like random separation to designing efficient algorithm in congest. It's also worthwhile to mention if we obtain a lower bound with respect to parameter like degeneracy, it also implies lower bound with respect to parameter like tree and vertex cover of that graph. So the good news is we also have efficient algorithm for computing orientation of a graph in congest. So there's a link between degeneracy and a cyclic orientation of graph. If we are given a graph G with degeneracy D, we can find a cyclic orientation of that graph such that every vertex in graph has out degree at most D, while the in degree can be still unbounded. And we can compute such orientation in log and rounding CONGEST. Let us start by finding the multicolored version of induced K tree, since usually using the multicolored version makes things easier in the case of reductions. So suppose we have a tree on K nodes labeled in bottom-up manner with K labels, such that the root has a label K and each children has a smaller label than their parents. And also suppose we have a graph G and the orientation of G and also K+1 coloring of G. Let H be a copy of T. We say that we say H in G is proper if the followings are satisfied. If every node in H with color I has a corresponding node in T with label I, and all nodes in out neighbor of some node in H has the same color 0. In this case, we are able to find a proper induced copy of T in the CONGEST. The algorithm takes off K rounds. Let me leave the lemma with that proof and just jump through the details of algorithm. So we have a graph of D degenerate, and we know how to compute the alpha orientation of that graph. So let's say 5D orientation of graph G. Remember, 5D orientation means every vertex in G has that degree at most 5D. We know that we can compute such orientation in log n rounds in CONGEST. And we iterate the following step for T times for each node V. If V picks color 0 with probability 1/2, and if it's not the case, then we pick the color from sets 1 to K uniformly at random. And by the setting of these two steps, we can also check if there's a proper induced copy of T with respect to such coloring by the previous lemma. So let's say we have a yes answer. So we know that there's a copy of T as an induced subgraph in G. Under the orientation, we know that every node in H has at most 5dk out degree, out neighbors. So the probability that we can find the coloring in G, which is proper, is at least 2 to the minus 5dk times k to the minus k. So it's enough to take T as 2 to the 5dk times k to the k times log n, and then we have algorithm to detect induced copy of T with high probability also. So in the case of running time, since we need log n rounds to compute the orientation, and also we iterate the steps for T times, so we have T plus log n, but we can get rid of the factor log n by the art of parameterization. So at the end, we get 2 to the 5dk times k times k to the k in total. But recall that this algorithm is still randomized. But since we are borrowing the method from parameters complexity, we can also use them to de-randomize the algorithm using family of perfect hash function. So at the end, we get a deterministic algorithm, which takes function of k and d plus log n rounds algorithm in CONGEST, rounds in CONGEST. In the case of other results, we have the following conditional and unconditional lower bounds for detecting induced subgraph for general graphs. when pattern contains clique and independent set, we have the followings. And also for the case of multicolored version problems, we use the previous results on multicolor K independent set and multicolor K clique. And in the case of maximum count induced subgraph problem, when parameterized by vertex cover number of the input graph G and H, we design deterministic algorithm that takes 2 to the S squared, 2 to the power of vertex cover number of the graph in the congest. So in the case of open question, a natural question that can be asked is, has been studying very well in the distributed case, but there are other parameters like tree width and path width with less study. So it's natural to ask about translate our result for tree width and path width. And the other open question can be about a framework that separates very well between non-induced and induced case in general. So as far as we know, we have the lack of such systematic result for this separation.
Thank you. So okay, so it's about distributed congest approximation of the weighted vertex cover and matching. So how is yours?
So, hi, I'm Marc Fuchs, and I'm going to talk about distributed congest approximation of weighted vertex covers and matching together with Salwa, Faour, and Fabian Kuhn. So let me shortly introduce the congest model. In the congest model, the network is modeled as a simple n-noded graph, where each node has a unique identifier of size at most O of log n bits. So in the congest model, the algorithm proceeds in so-called synchronous communication rounds, where each node is allowed to perform arbitrary computations and send messages to all of its neighbors, but the message size per edge, per communication round is bounded by O of log n bits. In the end, each node should know its part of the output. So for example, if the task is to have some node coloring on the graph, in the end, each node should know its color. All right, so let me shortly introduce the problems we handled in the paper. So the first is the minimum weight vertex cover. Here we have weights on the nodes, and the goal is to find a ZS. The ZS is actually our vertex cover, which is a subset of the nodes of the graph, such that each edge of the graph has at least one endpoint in the vertex cover. And since it's weighted, our goal is not to minimize the number of nodes in the vertex cover, but to minimize the weight of the nodes in the vertex cover. So for example, here's a simple graph, and the intuition would say this is our vertex, our minimum vertex cover, which is true for the unweighted case, but for the weighted case, this is not true since the node in the middle has a very high weight. And therefore, the minimum vertex cover here is actually every node but the middle one. Okay, so let's switch to the matching. In matching, we have weights on edges instead of nodes. The goal is to find a subset of the edges such that no two matched edges have a common endpoint. And here, the goal is to maximize the sum over the weight of the edges. So for example, here's the same graph with some edge weights, and the red marked edges form a maximum weighted matching. All right, now let's take a look on the state of the art and also what we provide in our paper. So for the minimum vertex cover, there is an unweighted deterministic bipartite 1 plus epsilon approximation to the vertex cover by my co-authors in the last year's OPODIS. Note that this algorithm I present later is some generalization of this one. So then there's an interesting deterministic algorithm, a 2 minus epsilon approximation algorithm by Ben-Basat, Kawarabayashi, and Schwarzman. And here, this algorithm is efficient if the optimal vertex cover is small. And further, there's a 1 plus epsilon approximated lower bound, which we show in this paper. And this lower bound is actually that we cannot approximate the vertex cover faster than log n divided by epsilon rounds for 1 plus epsilon approximation. So when it comes to the weighted vertex cover, there we have an efficient true approximation by Ben-Basat, Even, Kawabayashi, and Schwarzman. And we present a 1 plus epsilon approximation, but just on bipartite graphs. The first one is in general graphs. But note that we also provide some generalization to non-bipartite graphs, which you will see later. All right, now let's take a look on the state of the art in the case of matching. Here, for unweighted graphs, we have a 1 minus epsilon approximation, which has a runtime exponential in 1 over epsilon times some log delta factor. And just recently, by Fischer, Mitrovic, and Wito, they came up with an archive paper, which actually have also a 1 minus epsilon approximation to matching, but which is just polynomial in 1 over epsilon. It's, to the best of my knowledge, the first 1 over epsilon time-based algorithm to the unweighted matching so far. So for the weighted matching, there is a 2/3 minus epsilon approximation by Amadi, Kuhn, and Oshman, which works deterministically in general graphs. Note that in the same paper, they also provide a 1 minus epsilon approximation, but for bipartite graphs only. So and we actually have a 1 minus epsilon approximation for general graphs, which is exponential in the runtime in 1 over epsilon. All right. So what are the tools we use for our matching and vertex cover algorithms? The first tool is a clustering algorithm. So clustering, in some sense, reduces the graph into clusters with lower diameter. And the second, which actually was the idea of Rosen and Ghaffari. And then it was refined by my co-authors in last year's OPODIS, such that these clusters also have some white density, a 1 minus lambda white density. And what I mean with white density is the following. There are some nodes, which I marked here as the white nodes, which are not part of any cluster. And so there is some weight of some nodes, if you're talking about vertex cover, some node weight, which is not part of any cluster. And we want that to be small. And so we say that the sum over the weights of those nodes is at most a lambda fraction of the overall sum of the node weight. So this is our first tool we use. And the second one is of the Discs 18 paper of Amadi, Kuhn, and Oshman, where they provide a 1 minus epsilon approximation to the weighted matching in bipartite graphs. And this is what we need for our matching algorithm. And for our vertex cover algorithm, we use, with some slight adjustments, a 1 minus epsilon approximation to the fractional W matching problem. So what is the fractional W matching problem? So actually here, the goal is to find some values YE for every HE in the graph, such that we maximize the sum over these values. And so that for every node, these values over their edges is smaller equals than the weight of that node. So if you would substitute this weight by 1, this is just the classical fractional matching. So this W matching is some kind of generalization. All right, so let's start with the ideas how we get our results for the vertex cover. So I guess many of you know Koenig's theorem, which provides a constructive proof of how to get from a maximum matching to a minimum vertex cover in bipartite graphs. And there is some kind of generalization to approximations. So if you have a 1 minus epsilon approximation of maximum matchings without short augmenting paths, then we can construct the 1 plus epsilon approximation to the minimum vertex cover in that same bipartite graph, right? And this is in the unweighted setting. Now we have the weighted setting, and they're the equivalent to Koenig's theorem is here Egavari's theorem, where we need this maximum fractional W matching, which I just explained, and we can construct here a minimum weighted vertex cover in bipartite graphs. And also this one can be extended to approximations, so that if you have a 1 minus epsilon approximation to the maximum fractional W matching without short augmenting paths, we can construct a minimum weighted vertex cover, 1 plus epsilon minimum weighted vertex cover. So note that we compute this maximum fractional W matching by this algorithm of Amadi, Kuhn, and Oshman, which is based on linear programming and therefore has not the nice property that we do not have short augmenting paths and stuff like some other algorithms have. And so the first challenge is how to get rid of short augmenting paths. And the second challenge is that this, this construction has diameter time. So how we get rid of this diameter time? We don't want diameter time in general graphs, but since we use the clustering algorithm introduced, we can say, okay, a cluster has some polylog n size, and therefore it's small. The diameter is small. All right, so now, okay, first, what is a short augmenting path in the sense of, fractional edge weights? So an augmenting path here is an odd length path where every even edge has this fractional value ye greater than 0. And those endpoints of this path are not saturated. Means that the sum over their edges of this fractional values is smaller, really smaller than its weight. So this is what we call an augmenting path. So now, how to get rid of those augmenting paths? So actually, we do not augment those paths like we do in the unweighted settings. So what we do here is we slightly reduce the weights of the edges at nodes such that no such path remains. So let me make this straight. So we have our graph G, where we computed our maximum fractional W matching, where we have some short augmenting paths, which we don't like. So we construct a graph G prime with the same nodes and the same edges, but where the nodes and the edges have slightly reduced weights. And then we solve, then we apply our construction here to this graph G prime. And since we just slightly decreased weights and the weights, we still have a good approximation to the vertex cover in the original graph. Yeah, and that's basically the idea for our vertex cover, which then results in a poly log n divided by epsilon runtime. So now let's switch to the generalization to non-bipartite graphs. So the idea for non-bipartite graphs is pretty simple, but it just works for some subfamily of general graphs. You will see in a second. So let's assume we have a graph G, which is non-bipartite and weighted. Then we first construct the so-called bipartite double cover. I don't know if everybody knows what that is, but let me shortly explain. So for example, we have a green node here. Then we split every node into two, let's say, sibling nodes, And for example, this green one is here like these two siblings created of it, and every edge is also in the bipartite double cover, but always from a left sibling to a right and from a right to a left, such that the graph is bipartite in the end. All right, now we apply the algorithm I just explained, which works on weighted bipartite graphs, and we get some vertex cover approximation. For example, this would be some bad vertex cover approximation. And now we can transform this solution back to our original graph, which does result in a half integral solution. What does that mean? Half integral solution consists of values 0, 1, and 1/2. And if, for example, two sibling nodes are not in the vertex cover, we say the half integral value is 0. If both are in the vertex cover, the half integral value is 1. And if one of both is in the vertex cover, it results in 1/2. So now we have a 1 plus epsilon approximation half integral solution on our original graph. So now we have to convert it to an integral solution. So therefore we simply keep all the nodes with value 1. We discard all the nodes with value 0. And for the nodes with value 1/2, we construct an induced subgraph of the set of nodes which have this value 1/2. Now we find an independent set I on those 1/2 nodes. And finally, we discard all the nodes in this independent set and keep all the other nodes. And so if we can compute an independent set such that the weight over the nodes of this independent set is greater equals lambda times the weight of all those nodes, then this actually leads to a 2 minus 2 lambda plus epsilon approximation. So this generalization holds for all graphs where we can somehow compute this lambda approximated independent set, which should apply on every subgraph of the graph. Right. So if it's not handy enough, there's like some nice application for it. For example, coloring. Assume we have a graph coloring, and let's say we have a C coloring of the graph, and we know which color is the heaviest one. Heaviest in the sense that the most weight, it's the color with the most node weight. So then, of course, using this color class as independent set directly gives us a 2 minus 2 divided by C plus epsilon approximation. So this was our vertex cover algorithm. Now let's switch to our weighted matching algorithm. Our matching algorithm is based on the work of Lotka, Pachemir, and Petty, where we improve a given matching iteratively. So first, we construct a bipartite subgraph H from a given general graph. So here, for example, we have a general graph, and we have an initial matching. Okay, so now we construct the subgraph H in the following way. We color the nodes black and white. We keep only bichromatic edges, which means, for example, here's an example. There are two white nodes, and we have an edge. This one cannot be kept, right? And also here's an edge between two black nodes. We'll also not keep this edge. So for the nodes, we keep nodes. We do not keep nodes if they have a matched edge between them and if both nodes have the same color. So for example, here we have two white nodes and a matched edge between. So we just throw away those nodes for our subgraph, for a bipartite subgraph. So and you can see in this example that H actually is bipartite and a subgraph. All right, now on H, we apply the matching algorithm we use from our toolkit. And we approximate the matching with 1 minus lambda matching for some lambda which is smaller than the epsilon we want in the end for our general graph G. So here, for example, we found this matching, which is slightly better. And yeah, now we bring this matching back to our original graph. As you can see, it changed. For sure, one iteration is not enough such that we have 1 minus epsilon approximation. So we just repeat this process again and again until we have a 1 minus epsilon approximation. So now how can we do this in a randomized setting? That's pretty simple. We color the nodes black and white independently with probability 1/2. As the approximation we are looking for on the subgraphs, we just choose like exponentially small in 1/epsilon. And then we can show that in expectation, we do some progress in the matching. So for sure, if we sample randomly bad bipartite subgraph, our matching is worse than before, but in expectation, it is better every time we apply this construction. And so we can show that for some success probability, 1 minus delta, we have a runtime basically in exponential in 1/epsilon times log 3 of 1 over the success probability times some log delta plus log star n factor. So note that for constant epsilon and constant success probability, this is actually pretty efficient. If you want, and we can also go for high probability, but then we have here a log 3 n factor. Right, and we also provide a deterministic way to find those bipartitions. So therefore, this is a little bit tricky. What we want is to find T bipartitions such that every possible path of nodes appears in at least one of these bipartitions. So what does appear mean? Appear mean that a path like has colors black, white, black, white, black, white, so alternating colors, such that at least in one of those bipartitions, our matching algorithm has the possibility to augment that path. Right, and we can show by a probabilistic method that for t equals 2 to the power of k times log n, we have all such passes up to some length k covered. And we choose k in the end like 1/epsilon to achieve the desired approximation. So deterministic, we first cluster our graph, then we compute the colors deterministically, like I just explained. We approximate matching with the lambda even smaller than in the randomized version. We also have here an exponentially small value, 1/epsilon times log n. And now we go through all this bipartition and try to improve the matching. But now, since we have clusters, we can compare our current matching with the previous matching, and we now just keep the matching if it's significantly better. And therefore, we guaranteed have progress. And we cannot run in the case that the new matching is worse than the one before, like we have in the randomized case. Yes, and this leads to an algorithm, polylog n times 2 to the O of 1/epsilon. All right, so let me conclude with 2 open questions. So the first question is if it's possible to find such a matching approximation algorithm, for weighted matching approximation algorithm in time sub-exponential in 1/epsilon. And the second open question is if we can find a vertex cover algorithm which has an approximation ratio better than 2 in general graphs or even some other graph families. Thank you.